Yeah. That is true.
Ronita, can you hear us?
Yes, I can hear.
Okay, how are you? Did you travel okay? Safe
Yes,
journey to India?
it was really good.
Okay, good. Everybody okay in your house?
Yes, everybody is fine. Thank you so much.
Good to know. Good to know. So Ronita is leaving FAU, unfortunately.
Yeah, I know, yeah. And she told that she will miss you back.
Yeah, definitely.
All right. Whenever Purvita, let me know, okay, when you want me to start.
Yeah, let us wait for some 3 or 4 minutes because people are joining now. And Jasar is there.
Oh, Professor.
Is that MC sir?
Huh?
Is that MC sir?
Yeah.
Oh my God, MC sir? চিনা কতদিন পরে দেখলাম।
হ্যাঁ, কতদিন পরে আমিও তো তোমাকে কতদিন পরে দেখলাম।
কেমন আছেন স্যার?
হ্যাঁ, খুব ভালো, খুবই ভালো আছে। ঠিক আছে, খুবই ভালো মানে হচ্ছে মানে পার্সোনালি, আর চারদিকটা ইজ নট গুড।
রাইট আই নো। Good to see you, sir. Good to see you. It's been a long time.
আজকে তোমার টকের জন্য just waiting. Yeah,
thank you.
After a long time.
Thank you.
Also, Sanka Pranava, Papiya was my student in Kolkata.
I suspected that, by the way.
But meeting after a long time, maybe.
I left India 15 years, so it's 15 years.
Wow.
Only? It is more.
No, it's 15 years. Yes. Yes.
You are expecting more, I guess.
It's long for me, but yeah.
You haven't gone back?
Long for us. Sorry?
Papiya, you haven't gone back to India in these 15 years?
I have, yeah, many times, and my parents came too. This is the first time that I haven't met with my family for 3 years, consecutive years. First time ever. I tried to meet with them every year. I'm the only child, so obviously it's really hard for us to be away from each other. But this is the first time because of COVID, I'm stuck and I cannot go home. They cannot come. It's just a bad situation.
Yeah. Hopefully it will improve soon.
I really hope so, yeah. And I have 2 kids, and you see that they're the only grandkids of my parent, and my kids are growing up, and my parents are missing all of that, and they're like, it's like bad, emotionally, it's like not good.
I know, yeah.
But yeah, I hope so too. We all hope that. Yeah, Ronita, I cannot go to India this summer, I'm pretty sure. I think you probably already guessed, because she was asking me if I come to meet with her, but I don't think I can. I don't think I'll be allowed to. That's the thing.
Yes, I know you can't come. Difficult.
Yeah, I think I won't be allowed to come back to US.
Let us hope for a miracle.
I know.
Yeah, that is the only hope we can do.
Yeah. There is some talk about.
Stay safe. Like I was saying, my family, this is the first time one of my immediate family members just passed away 2 days ago. So I am, yeah.
I'm sorry to hear that.
Yeah. So anyway, all right. Whenever you are ready.
In Kolkata.
Yeah, maybe we can start now. Okay. So it is my great pleasure to introduce Papiya Bhattacharjee in this webinar. I'm so happy that we are getting her as a speaker today. And he is currently a graduate faculty of Florida Atlantic University in the USA. She actually completed her master's from University of Calcutta and received her PhD from Bowling Green State University. And she is the mother of 2 children. And she actually yearly organized, it's yearly, right? The conference, namely Ordered Algebraic Structure and Logic, that is OAL. And yeah, today she is going to, I just forget the title of your talk today.
It's okay.
So, yeah,
I should probably share the screen.
Some, related to frame theory. And it's over to you, Papiya. Please continue.
Thank you. Thank you so much for inviting me. I'm really, really glad that I can talk here, and it's my pleasure. Can everybody see the screen I'm sharing?
Yeah.
Okay, thank you. Yeah, so I was at Penn State for 10 years, and then I just recently moved to Florida Atlantic. Many reasons, but yeah, I got tenured in Penn State, then I moved here, and now I'm at Florida Atlantic. So I'm going to talk about M-frames and minimal prime spaces. Let me see if I can change the page. Yes, I can. Okay, so a few topics, but I want to talk about quickly a little story. I like to tell stories, right? And people who know me know that. Just a little bit. So my advisor, my PhD advisor is Warren McGovern. I don't know if you guys know his name. And so he was in Bowling Green. That's where I went, and that's who I worked with. Warren's, Dr. McGovern's advisor, so my mathematical grandfather is Dr. Jorge Martinez. And his advisor, so my mathematical great-grandfather is Dr. Paul Conrad. So Professor Conrad is kind of, we can say that he was the father of this lattice ordered group theory. Okay, he worked on that area, is very big in that. So Conrad was working in lattice ordered group, and at the same time, parallelly, Banaszewski was working on frames, if you know Banaszewski's name. And they knew each other, and they, I think I heard the story that they were fighting in World War II and everything, you know, against each other. Anyway, that's a different story. But the reason I started this, so Martinez, Professor Martinez, who is Paul Conrad's student, he of course worked on lattice ordered group, but then he also did a huge amount of work on algebraic frames. And when I started working with Dr. McGovern, I really got influenced by Dr. Martinez's work, and I really worked on frames, and especially algebraic frames. So the reason I'm saying this is because I am, I don't know if you guys know this or not, but Dr. Martinez just passed away last year, very, very recently. And it really hit me a lot. I met the guy, I met him many times at my OAL conference. He was the one who started the OAL conference annually. And then I kind of took over, and he passed away recently. He was very sick. He was in nursing home for a long time. Anyway, so this talk is dedicated to him. And this year I'm going to give a few more talks. It'll be dedicated to Professor Martinez. So yeah, so that's what I wanted to say. Okay, so we're going to talk about frames a little bit. Quick, going over to concepts here. So we start with a lattice. Lattice is a partially ordered set where every two element will have a supremum and an infimum. So supremum is the least upper bound, infimum is the greatest lower bound. So we will use this the sup notation and the wedge, the int notation. So we start with a lattice, and for it to be a frame, the lattice has to be complete. Complete means not just finite inf and sup exists, but any arbitrary inf and sup will exist in the set. And then the lattice also has to be distributive, just the distributive, usual distributive property with the inf and the sup. Okay, that has to be satisfied. So then a frame is a complete lattice, which is distributive, but not just that, it has to be more than that. It has to have a strong distributive property. And the strong distributive property is the finite infima distributes over arbitrary suprema. Okay, so we don't need the arbitrary infimum to distribute, but just the finite infima and distributing over arbitrary suprema. And where this comes from, I'll tell you, the motivation is actually from topology. So I'll get to that. So see, since the lattice is complete, the frame is complete, it will always have a top element, the highest. And I always look at lattice as a picture. It has a top element, we call it 1. It has a bottom element, which we call it 0. So you can think of, supremum of all the elements, that's the top. Infimum of all the elements, that's the bottom. And think of it that way. So it always has that. So it's a bounded lattice. Okay, just a quick example. I couldn't stop myself from drawing a picture, so I got excited and drew a picture in LaTeX. So if you take 3 elements, take the power set, it's a discrete topology. Then all the points, the those are the elements of the lattice, and that forms a frame. This is actually a Boolean algebra, and any finite distributive lattice, I think I wrote that down. Yeah, it doesn't have to be just this Boolean algebra. If you have any finite lattice, which is also distributive, it has to be distributive, then it's a frame. So any power set of any set of elements will always be a frame. It's a Boolean algebra. So when you talk about set, we use the subset subset notation, but that is the less equal to relation that is in lattice. So the subset becomes the less equal to. Okay, so that's an example. So the other examples of frames. So frames come from various areas of algebra and topology, which is what I really like about it. It's like a general concept. So originally the frame was called as point-free topology because the motivation came from topology. So you take any topological space, okay, look at its open sets. So basically the idea is look at only the open sets, ignore all the points. That's why point-free. And the collection of open sets will satisfy the property of the frame. That's why we have that strong distributive law. So if you think about it, okay, we know that arbitrary union of open set is open. So we have the arbitrary supremum. Now the intersection of finitely many open set is open. So we have finite inf there. We don't have arbitrary inf, right? I mean, not directly. Arbitrary intersection of open set is not open, but guess what? There has to be an infimum. The infimum turns out to be the interior of the intersection. So take all the intersection of all the open sets, then take the interior. So that's an open set. So that's the infimum. But guess what? The topology satisfies the strong frame law. So if you take, A intersect arbitrary union of B alpha, it'll pass through. It'll be union of A intersects B alpha. And that's where the motivation of that frame law came. Okay, so frame came basically from the topology idea. I don't exactly know if anybody knows, you can correct me. I exactly don't know the name, why the name frame has been used, but I feel like it's like the framework of topology. Like you are considering just the opens and ignoring the points. It's like you're considering the frame of a window, without anything else. That's probably why that name has been used. People would call it I think I read a paper at the very beginning, they were starting to call it pointless topology, which is such not a good name, pointless topology, So they started saying point-free topology, and now it's called frame. Anyway, so that's the big example. But then guess what? Frames come from rings. If you take a commutative ring with identity, the radical ideals, the collection of radical ideals, that will form a frame. Under inclusion. So again, the inclusion is the less equal to. So you can get, if you like to study ring theory, commutative ring theory, you can get frames there. This frame has more properties. I'll talk about it a little bit later. Banaszewski is big in studying the radical ideals, and he has his big theorem there. Anyway. And then the last example, and this is why I think Professor Martinez was interested in working in frames, because frames come from lattice order group. So if you have any lattice order group, which is a group also has a lattice structure and they work well together, then the collection of all convex subgroups, the convex lattice order subgroup, that forms a frame. So if anybody works in rings of continuous functions, that is a lattice order group, and then you can get frames from there. So that's a big example of L group that people study.
May I ask something?
Yeah.
Yeah. Actually, the thing what I know that like this lattice order group is very much related with the idea of many-valued algebra. So my guess was that it came after many-valued algebra. Is it the case, or it was studied like individually as well?
I think it was kind of a parallel thing. It was going on, and then people found the connection between them, that you can go from one to the other. Yes. Yes, I think Mundici is one of the people who work in the MV algebra. Yes.
Yeah. Okay, thank you.
Papiya, I have one question here. So the definition of frame is that every element will be distributed over the arbitrary union of other elements?
Not just every element, every finite inner infimum will distribute over. Any finite infimum will distribute over arbitrary supremum.
Okay, so in this case, it will, because the arbitrary infimum is the intersection of them will be open again, right? Finite intersection of open set is open.
Yes, finite intersection of open set is open, so we can consider finite intersection, and arbitrary union of open set is open, so we can have the arbitrary union.
Yeah, so in this case, intersection of interior of finite of them is just them, right? Interior
yes.
of finite. Okay, okay, it makes sense.
Correct.
Yeah,
correct. Yeah. Yes. Okay, so see, because frame is a general, right? It comes from topology. Here is coming from a ring theory. So we can generalize various topological concept and ring related concept for frames. So first example, what I'm trying to say, compactness. We all know there is a concept of compactness in topology. If you really think about the definition of compactness, it deals with only sets, open sets. Therefore, we can just translate that definition for frame. Whenever there is a definition that doesn't have points and it only can be defined by open sets, we can translate everything in terms of frames. Okay, so here is a very good example, compact. Okay, what do we know about a compact set? Think about it. Okay, by the way, when we're considering the frame, we're only looking at the open sets, not any set, right? Only the open sets will form the frame. So you think of a compact open set if you consider. What do we know the definition of a compact set? If it is covered by open sets, then it'll have a finite subcover, right? Any open cover has a finite subcover. Now think what that really means. Okay, take a set, let's say C. Compact means when C is contained subset of a union of bunch of open sets, then it'll be subset of union of finitely many of those open sets. Look, that's exactly the definition. Take a point C, when it is contained in, which becomes less equal to, union becomes supremum of bunch of xi's, which are other open sets, then it will be contained in finitely many union. That's exactly the definition. We are just generalizing it for frames. This will play a huge role in my talk, and whenever you work with algebraic frames, you will see why. We use this notation K of L to denote all compact elements of L. Okay, so now the main one of the main thing is the M-frame. What is an M-frame? So first of all, you take a frame, we call it algebraic if every element is a union of compact elements. So basically it means the compact element is like a base, is generating all the other elements in the frame. Okay, so any element in the frame can be written as a join of compacts. So there has to be lots of compact elements in my frame in order for it to be algebraic. Furthermore, if you just recall a little bit of topological property, I will get very topological because that's what happens. I work with algebra, but the interplay of algebra and topology, that's what makes the frame theory so interesting to me. So if you take any two compact sets, their union is always compact. It's a well-known fact. You can easily prove it. Very simple. Intersection may not be. Okay. So in frames too, if you take two compact elements, their sup will always be compact, but their inf may not be. So we are using this extra condition. We are saying a frame will satisfy finite intersection property, or FIP, if given two compact elements, their inf is also compact. And lots of examples we have, most of the examples we work with, that it satisfies the FIP. Okay. Now, an M frame is an algebraic frame that satisfies FIP. Okay. So, in the literature, you will probably see people are just using algebraic with FIP, algebraic with FIP. I also did that, but then I started calling it M frame. Not just me, a few of us started calling it M frame because we are dedicating this type of frames to Professor Martinez. That's why I started with my story. So because of Martinez, we're calling it M frame because he really worked with this type of frames a lot. He has lots of paper on algebraic frames with FIP. So that's why I will keep calling M frame, and then hopefully people will pick it up in the literature and they will agree to that name, let's say. But okay, so M-frames, guess what? Any discrete topology will be an M-frame. There are other topologies also, algebraic with FIP. The examples that I told you, the one that coming from the commutative ring, the radical ideas, that is an M-frame. That is more than an M-frame, actually. That is also a coherent frame, which means, so the top element is compact. Okay, the top element compact means the whole set is compact. Okay, in a topology, if the whole set is compact, then the top element will be compact. So the radical ideals is a coherent frame. And Banaszewski has this great important result that any coherent frame is the radical frame of radical ideals of some commutative ring with identity. So you are studying coherent frame, you are just studying radical ideals of commutative rings. So and the C of G, the lattice order group, you know, the frame coming from there is a M frame. It's an algebraic frame with FIP. The compact elements are always the finitely generated one. For discrete topology too, the compact elements are the finite sets. Okay, that's the compact, because then any set can be written as a union of, you know, the singletons, and they are all compacts. Same with the radical ideas. Sorry.
Can I ask a question?
Yes.
Yeah. So is this FIP same as the one used in topology?
No.
No, isn't it? Yeah. So this is like KL is a meet semilattice. That is the statement here.
Yes, scale is a meet similarity. You're right.
So why is it called FIP? Because it is generally.
I don't know. That's a good question. I don't know. Dr. Martinez called it FIP and I think maybe he is the one who started calling it. But I'm not sure. And you were right. I also thought it might be a little confusing because there is a finite intersection property, well-known property in other areas, but I really can't answer that. We just started using that in the literature, and that's it. That's all I know. Yeah, go ahead.
I think, you know, this property was also used in connection with ultra filters.
Yes, it does.
And yeah, that is where it comes from, I think. Originally.
Okay. That probably, you're probably right. Yes, I know it is also used in ultra filters. Yes. But you are right that, okay, so because you brought it up, I will tell you that the compact element that is a it is a joint semilattice, sorry. It starts with a joint semilattice that has the 0, the bottom element, because the join of any two compact is again a compact. But because I am using FIP, I'm also including that property, it becomes a lattice.
Right.
Because then the inf will also be there. But it will not guarantee that for algebraic frames with FIP, it will not guarantee that the KL will have a top element. It's not a bounded lattice. It may not have the top. If you have a coherent frame, then yes, it is a bounded lattice, everything. But for my case, it's not bounded.
What is coherent frame?
Amit, did you ask me something?
Yes. So can you please define a coherent frame?
Oh, yes. A coherent frame is algebraic with FIP, and the top element has to be compact.
You define compact, yeah?
Excuse me?
Did you define that to be compact or compact M frame, or this is the definition of compact M frame? I was just between compact and coherent frames.
A compact M frame is a coherent frame.
Okay, thanks.
Yeah, and by compact frame, I mean the top element has to be compact.
Okay, thanks.
Okay. But for all the results that I will talk about, I don't work with coherent frame. My top element may not be compact. So I am relaxing that condition. So it's a little bit more general than coherent frames. Because my example also comes from the lattice order groups and other topologies where the top element may not be compact. Okay, just a few more things. I see I've taken a lot of time already. Pseudo-complement is a very important concept in frames. So basically, it's probably better to think about it in topology first. So take your topological space X, okay? Take an open set O. All right. I am looking for the largest open set that's disjoint from O. That's the complement. Not the complement, that's the pseudo-complement. Because, see, if you have an open set O, its complement is closed. So obviously that cannot be the one. So we cannot have a complement. We can think of, so how to think of the largest open set disjoint. Okay, you have a O, take its closure, take the complement of the closure. You see the picture? That's open. And these two are disjoint, of course, this O and that one. And that's the largest one that is disjoint from O. So that's the pseudo-complement. We call it XPAR. See how it is defined for frames? You look at all possible elements in the frame that intersect, the infimum is 0. So intersect empty and then take the join of all of them, union of all of them. That's the largest one that is disjoint from X. That's called XPAR. In ring theory, if you're interested in that, the XPAR really translates into the annihilators of an element. Annihilators of an ideal is the annihilator. Okay, that's the XPAR. And for topology, I just described what XPAR is. So always X inf XPAR will be 0. And guess what? That result, X inf XPAR 0, needs the frame law, because you have to distribute over an arbitrary union. So frame law is used right here. Okay, just quickly, we have a concept of density. So an element is dense if it's polar. Let's call it polar, the pseudo-complement. We call it polar, the perp. The pseudo-complement is 0, just like the dense open set in topology. So a set is dense means its closure is everything. Think about it, right? An open set dense means its closure is everything. So what is the largest open set disjoint from it? There's nothing left. It's empty set. So its polar is empty. So that's where the same density coming. So see, all this concept in topology can be translated for frames. And just a few things that, always an element and its polar, if you join them, that is always a dense thing. I mean, if you think about it in topology too, it will be true. And then the reason I'm talking about it is because we call this unit. So if you have a dense element, which is also compact, we call it a unit. And that actually comes from lattice order group. They have L group always has this weak order units. That's the same concept that we need here for frames. Okay, so usually, mostly my M frames that I work with, usually we need to have a unit, because you will see the results I'll talk about, they always units come up. So all M frames are considered to be with a unit. So we have algebraic, we have FIP, and we have a present of an unit. So a compact dense element. Okay, now those are the properties that are generalization from topology, but guess what? We can also have things generalizing from rings. So for example, as we know, we have prime ideals in a ring, we can define prime elements in a frame the same way. Because the ideals, the structure of ideal form a lattice, so that lattice structure can be used as well. Okay, so what is a prime element? It's first of all, it's not the top element. So P less than 1 means we don't consider the 1 is prime. And then we are saying this for any two element, if the infimum is below P, so here's P, if the infimum of two things is below P, then one of them has to be below P. So if you think of the ring theory, the definition is AB inside of P means A in P or B in P. So the product changes into the inf here. Okay, same exact translation basically. And then we have minimal primes, because my talk is going to be about minimal primes, which means it's a prime. There is no other prime below it. That's the minimal. You can use our usual Zorn's lemma argument to show that primes and minimal prime exist for algebraic frames. Okay, the presence of a compact can help you figure out that there is prime and minimal prime. And this is the very usual notation. Spec is all primes, min is the minimal primes. Just a quick result to let you know that our algebraic frame kind of behaves like a semi-prime ring. The infimum intersection of all minimal prime is 0. Okay, so we have that result as well. I'm not going to describe in detail, the proofs and stuff, but just to give you some ideas of what kind of properties we're using and how they're parallel to in rings and in topology and L groups and stuff. Okay, so I thought I will give a quick example so that you have a picture of primes. Okay, so you can kind of understand what primes are like. and this is just finite example, finite situation, finite frames. So look at the right one, the frame F. Okay, I want to find out the prime elements. Okay, so look at the point C. C is not prime because see A and B inf to C, but neither of them are below C. They're both above and they're infing to C. So C cannot be prime. Same with the 0. 0 is not prime because C and D inf to 0, but neither of them below 0. So you can very easily see from a lattice structure, you can very easily point out which ones are not prime and which ones are. Anytime you have a thing coming down like that, that point, that element is never going to be prime. So primes are A, B, D. That's it. Not 1 because we don't consider 1 to be prime. So A, B, and D are prime. And minimal will be D and A. There's nothing below A that's prime, and there's nothing below D that's prime. So those two are the minimal. Okay. For a chain, this is a chain. So you don't have that structure. So everything is prime, but not 1. So A, B, and 0, and therefore 0 is the minimal. Okay. If 0 is prime, 0 is always the minimal prime. And also notice that anytime you have a finite frame, it's going to be MFrame because everything is compact. There are only finitely many elements. So every element is compact. And so of course it's algebraic, of course it has FIP, everything is compact. Okay, so we can deal with finite frames and they're always compact. Always algebraic, sorry. Yeah.
It is even coherent, isn't it?
And they're coherent. You're right, exactly, because 1 is also compact. Yeah, exactly. Okay. All right, now I start. So what I did, oh, by the way, so I was writing this talk up, and when I decided, I thought, okay, I had my paper, my first paper was on these minimal prime elements after I did my dissertation. And actually the first paper got published after my second paper, by the way. So it's kind of my second paper, whatever, that is another story. So I was looking back, and I was writing this talk, and I'm like, okay, I had a few open questions for myself in my dissertation, and I tried to answer them later. And in this paper, I did answer. And then I thought I'm done, and then I looked back writing this talk and I realized, oh my goodness, there are still some questions I haven't answered. So maybe today I'm going to post those questions and see if anybody gets interested, and maybe somebody will work on it, or maybe I'll figure it out. I don't know. So there's still open questions from my dissertation. That was 14 years ago. No, 1, 2, 3, 15 minus 4, about 11 years ago, maybe. I don't know. It's kind of embarrassing, right? I still haven't answered my own open questions, but that's what it is. All right. So let's go over this a little bit slowly. What I'm going to do is I have minimal prime elements. I am going to put a topology on it. So it's a topological space. It's pretty well known. It has been done for rings already, L groups, and then I was doing it for frames. Okay, so the very well-known topology is the Zariski or the Hull kernel topology. You probably have heard that name. It comes up many places. So I'm going to put that on min L, and this is the way to do it. So we start with any element x in L. We define this set U of x. What is U of x? It's all those minimal primes. X is not below. X is not below P. Okay. Turns out that the U's have very nice properties. The union of two of the U's will be the U of the join. So basically the same notation follows, the union and the join. Intersection will be the inf. Very easy to show. I actually wrote down the proof thinking that I can quickly go over. So think about it, right? Take a prime P in the union of U and Ux and Uy. Okay. That means P is in one of them. Let's say P is in the U of X. What does that mean? That means X is not below P. Okay. I have to show P is in U of X sup Y. So I know X is not below P. Therefore, X sup Y should not be below P, because if it was below P, then X is smaller than X sup Y. It will be below P. Can't happen. Done. Very, very simple argument. On the other hand, take P in U of X sup Y. So X sup Y is not below P. Okay. I have to show one of these is not below P, right? X or Y. What if both of them below P? What if X is below P and Y is below P? Oh, by the least upper bound, X sub Y will be below P then. We can't have that. So if X sub Y not below P, one of them is not below P, and therefore we're done. So like I said, very simple argument with the idea of the least upper bound or greatest lower bound, and you can show this. Furthermore, guess what? Not only finite union, the U has a very good property. Arbitrary union also pass through. Any arbitrary union of U, you can show is U of the sup of X alphas. And furthermore, when is U of X empty? Okay, so that means what? That means there is no prime in this U of X. Okay, no prime in there. That means that X has to be below every single prime. Because if X is not below one of them, then that P will be in there. So X is below every prime. Guess what? We have the property that the inf of the minimal prime is 0. So the only thing that is below every prime is 0, is below the infimum. So X has to be 0. And if X is 0, 0 is an element which is below everybody. So of course below every prime, and therefore UX is empty. So both direction. So U has this wonderful property, and it'll show up why this is important. Okay. All right. So take an MFrame. Let me show the lemma, and then I will go over what I wrote before. If you take the collection of all the U of K's, K is compact. So not U of all the X's, just U of the compacts. That will form a basis for a topology. Okay, if you recall, to show basis, we need to show two things. We need to show that this collection covers the whole set, and something about the intersection. If you remember, basis means take two basic elements, intersect them, take a point inside, then you'll find a third basic element containing the point inside the intersection. We're going to show something better than that. We're going to show intersection of two of them is another one of them. Okay. So that's what I wrote here. First of all, see how it will cover. Okay. Remember, we have algebraic property. We have algebraic. So if you take the top element 1, by algebraicness, we know that the 1 can be written as a union of bunch of compacts. Okay, compacts generate everything. So 1 is the sup of K alpha. Okay. Take U of 1. U of 1 is the entire minimal prime because 1 is not below any P. So all the minimal primes in here, okay? But then is the U of the sup, and then we can carry over is the union of U of K alpha. See, all the U of K alpha will union up to the whole set, min L. So it covers it. And then, like I just said, intersection of two U's is again U of C in D. And here I need FIP because I don't know otherwise C in D will be compact. So FIP will guarantee that the intersection is back in that collection. And so it is a basis, and it is a basis for the Zariski topology, the Hull kernel topology. Very important topology, like I said, is well known in literature already. If you look at Hendrickson's paper, you will see in C of X, he talks about the minimal prime ideal spaces with the Hull kernel topology. Okay, he has worked on this a lot. So it is already known, and I can show that for frames too, that for min L is going to be Hausdorff. It's already Hausdorff and is 0-dimensional, which means it has a base of Klopen set. Guess what? These UKs, they're all Klopen. They're not just open, they're closed as well. And so it's a Hausdorff and 0-dimensional space already. Okay, so this is known, and I'm talking about this is known for rings, for C of X. Now, there was a big question at this point. When is this a compact space? That was the question, okay? And that was my first question I was looking at for frames. When is min L compact? Because we want to know that, right? Whenever we have a Hausdorff space already, we want to know when it's compact, we want to know all the different properties. So I went very topological here, looking at min L and figuring out all the different topological properties of min L. So just to give you a quick history also. So this is what I was talking about. See, Hendrickson-Jerrison's paper in 1965 is dealing with this question, the space of minimal prime ideals of a commutative ring. When is that compact? And they answer it there. Okay, is the complemented ring is the answer. If the ring is complemented, then it'll be compact. And then Conrad and Martinez, they answered the same question for lattice order groups. See, complemented lattice order groups, they answered when the mean of the lattice order groups, minimal prime subgroups, that topological space, when that is compact. And they found out, oh, it's the complemented lattice order group, just like complemented ring, same thing. So here's the thing. These proofs, especially the lattice order group proofs, is quite complicated, to prove that the space is compact if and only if it's a complemented lattice order group. I think they use transfinite induction and all sort of things. This pretty complicated. And then my advisor, McGovern, he in 2006 published this paper, in this neat rings paper, where he had found a much better way of proving the result. He actually figured out, guess what? We need to consider a completely different viewpoint. And he figured out that, and I will tell you exactly what he did and how I generalized that. You can actually have a different topology on this space, mean L, and use that to prove when that space is compact. So I was writing my paper. This is my, like I said, my first paper, which actually published second in 2012. Finally, it got published. That's where I have all this result written down. So it was a funny story. My paper, I submitted it and I didn't hear back like for a year or so. And I was new, I didn't know that I was supposed to actually contact the person and ask what's going on. So I was told you should contact, so I did. And then they said, oh, by the way, your result on this, when is the min L compact? It actually is very similar to a paper, 1974 by Speed. See, nobody knew this. Nobody knew about this paper. And it turned out that that method that the McGovern used even has been used by Speed. And nobody realized, because he wasn't really talking about frames. He was looking at Browerian lattices, dual spectral, all sort of, it's very hard. Sometimes in literature, things get lost because of that, because they don't, the terms are not there. You cannot even find it. Thank goodness whoever my referee was, he or she realized it and told me about it. So now in in our group, everybody knows Speed's paper because now he realized it. So he didn't do much with it. He didn't do anything with this. He didn't even realize it's actually another topology, but he did use that method. So that's why I put Speed's paper here. And if you read my paper, you will see I give him all the credit, because obviously he already did the work, at least some of it. And we are just expanding on it. So here it is. So I still remember when I went to my first OAL conference, 2007, I think. And it was, Martinez was organizing it in Gainesville, University of Florida. And I was going to give a talk on this mean L compact. And my advisor couldn't go, Warren couldn't go. And he told me, make sure you mention in your talk how much simpler our proof is than their proof, because Martinez was sitting in the room. And I remember I had the guts to even say that, that this is I didn't say it in that way, but I did say, it's a simpler proof than the proof in this paper. And I remember Martinez stood up, and looked at my proof very well, and later came to me and said, yeah, you did a good job. I feel so ashamed, and I was so shy. I was like embarrassed almost. Like, sorry, your student told me to do that, so I did it. Anyway, so here is a great way of showing that mean L is compact and when it is compact. So what happens is we can define another topology on mean L, which people didn't realize for a long time. What you do is you take the complement of the UX. See, the UX we already defined. Those are the open sets for the Hull kernel topology, the Zariski topology. Now you consider the complement of it, the V of X. It's all the minimal prime. X is below P. This V operator also has this nice property, but see, the things are switching, right? The union becomes the inf, intersection becomes the SU, because they're the closed set basically for the Hull kernel. But it turns out that they will also form a basis for a different topology, and we are calling it the inverse topology because that's kind of the inverse of the Hull kernel, and we denote it by min L inverse. And surprisingly enough, this topology turns out to be not Hausdorff, it's T1, and it is compact. It is a compact space. Then the proof or the whole theorem, when is the Zariski topology compact? If and only if the two topologies are equal. Min L is equal to min L inverse. And that makes the proof so much easier. We don't have to do transfinite induction. We can just go through another topology showing that they're equal to each other. And this last result or the statement, that is the complemented statement, which we know for rings, for L groups, and for frames, it follows true. But the proof is so simple. So complemented means this. Given a compact X, you can find a compact Y. Their inf is 0, so they are disjoint, and their sup is not everything but a unit. So it's dense, it's very close to being everything. And this concept from C of X, it comes from the co-zero complemented. That's exactly co-zero complemented spaces. Given a co-zero set, you find a separate co-zero set, which are disjoint, union is dense. So the co-zero complemented is the complemented frame, the complemented ring, the complemented lattice ordered group. So the same concept, okay? But the proof that that middle part made it so much simpler, that the two topologies are equal to each other. And that gave us a lot of other things to do now, right? Now you have a topology, a new topology, inverse topology. Figure out things about it. What do we know about it? We know it's compact T1, that's it. Okay, so I started looking at the inverse topology then. Now, see if we satisfy this property, so if our frame is complemented, the inverse topology has all the properties of the Hull kernel topology because they're equal to each other, and it actually becomes a stone space. It is compact. Sorry, it doesn't become stone space. It becomes a Boolean space. So min L inverse is now going to be compact, Hausdorff, and zero-dimensional. So that's a Boolean space. So my goal was characterizing when is min L a stone space and min L inverse a stone space. And stone space means compact, Hausdorff, extremely disconnected. Extremal disconnected means closure of every open set is open, is Klopen. So that's extremal disconnectedness. If you have all three properties, then that topological space is called stone space. So that was another big thing about min L, because we know now when it's compact, it's already Hausdorff. So when is it extremely disconnected, then all three together will be a stone space. So I looked into those as well. But before that, realize that we need to know a lot more about min L inverse. We just know that it's compact and T1. That's it. Nothing else. So very first question is, when is it zero-dimensional? Okay, so I answered that question. When is min L inverse zero-dimensional? That means it has a base of Klopen sets. And it turns out that this condition here. So conditions are getting complicated now. I think this is in the literature for rings. This is called weakly complemented. So the complemented gives you the compactness of min L. Weakly complemented is the min L inverse is zero-dimensional. So I can quickly show you, I always like to do these hand movements, what this condition is saying. So if complemented was given an A, you find a B, they're disjoint, sup is a unit. Okay. Weakly complemented is given two A and B, whose inf is 0 already. So they start with disjoint, two disjoint A and B. You can jack it up. You can find X and Y above them, which are disjoint, and sup is a unit. So those A and B are not units, but you can jack it up to some X and Y, they're disjoint, and their sup is a unit. That's the weakly complemented. Of course, complemented implies weakly complemented. So that gives me, okay, I get zero-dimensional now for min inverse. Now notice that if you have a zero-dimensional T1 space, it's a Hausdorff space. So my big question, and that was why my first paper got delayed, because I was asked this question, when is the inverse topology Hausdorff? And I was thinking about it. That was actually my open question in my dissertation. And that seemed to be pretty hard. I could not find it. It took me a while. So when is inverse min Hausdorff? And now we have so many different papers on this particular topic. We did this after the frames. I worked on it for L groups and for rings as well, but I do have a result. Turns out that because it's already compact, Hausdorff and compact will make it normal. And then we started calling it Lambron. That was not in my paper. This paper, the frame theory paper, actually later we found this name. See, you can read normal from the other way. So we just came up with that name. You see that? Normal. Yeah, we just reversed it because it's inverse normal, so we call it Lambron. So very complicated, but basically, see, remember the weakly complement. So this is weaker than that. So what happens is if you start with A and B, that is into 0, you jack it up to X and Y, but now the A with the X is into 0. The B with the Y is into 0, and X sub Y is a unit. So it's weaker, but it's a little bit, more. So it took me a little bit time, but I finally found out, and it was a great satisfaction when I found this condition. At least I have some internal condition for Hausdorff for frames. Okay, so that was that. Now, stone space. So remember, our goal was, when is it a stone space? And the stone space means for min, I just needed to figure out when is it extremely disconnected, because I know when it's compact. I know it's already 0-dimensional. So we need compact 0. What did I say? No, we need compact. I forgot already. Stone space is compact, Hausdorff, and extremely disconnected. Yeah. So mean is already Hausdorff. I know compact. Now we have to figure out when is it extremely disconnected. So remember, extremely disconnected means closure of every open set is again open. So a few things about the Hull kernel topology on mean L. I want to quickly talk about it. So it turns out, if you take a basic open set, C compact, U of C, is V of C perp. They're the same thing. And there's a result we can show that anytime you have a set that has V in it, in Hull kernel topology, any V of X is closed. Any V of X is always closed. So U of C, that's open already, is basic open, but it's also closed because it's V of somebody. Therefore, it's open. Okay. So therefore, closure of the U of C is U of C itself, but it's also V of C perp. So closure of U of C is V of C perp for C compact. Guess what? Turns out it doesn't have to be compact. Take any X, closure of U of X is V of X perp. So that's an important result, because now I know, okay, what does it mean by extremely disconnected? All of these guys should be open. That's all. Because that means closure of every open set is open. So all the Vx perp, when it's open, that's extremely disconnected. Anyway, but that translates into something nice. So this is the result for when is mean L stone space, if and only if these are all characterization. Stone space will happen if, see the complemented type situation happening, but this is for all X in L. Complemented happen for compacts only. Given a compact, find a compact, inf is 0, sup is unit. Here it says, given any X, find a compact, inf is 0, sup is dense. So for any X, you can find kind of a complement of it in the basic elements that will make it happen. So nice result for mean L being stone space. Very nice. My goal was to figure out a similar characterization for mean L inverse, and I could not. So this is still an open question. I still haven't figured out when is the inverse topology on min is a stone space. So I got stuck finding out a characterization of extremely disconnected. That was even harder for mean L inverse. So in the last bit of my talk, I know I have probably 5 minutes left, right? I'm gonna just give you a few other viewpoints that I figured out how to look at the inverse topology. And I'm still trying, to find this answer from that viewpoint if possible. So one viewpoint for inverse topology. So this is something I figured out, and this is in that paper as well, the frame paper. And I think I have never talked about it. In all my talks, I never gave this talk. So what you can do is, we have a MFrame L. If you just look at L, it's not gonna help. You have to look at a subframe of that L, and I'm calling it L prime. And the subframe is generated by all the polars of the compacts. So instead of looking at just the compact, you look at the C perps and the supremum of those C perps. then you can show that, you know, there is 1, there's 0, it's closed under supremum, is finite infimum, and it's a subframe of L. And in that subframe, you can define the L, the pseudo complement that we are defining L per. You can define that for the subframe. So almost like a what do you call that term? So I'm calling it L star. So it's like contracting down. You know, the pseudo complement that is in L, you're contracting down to that subframe. Using that, I can show that in inverse topology, the closure of every open set will be V of L star. So it goes parallelly with the Hull kernel topology situation. But you cannot use the perp, you have to use the star. You have to use things from the subframe, okay? Okay, so I can have an extremely disconnected theorem using this subframe. I'm not happy, you know, I'm not satisfied. I need something from L because I cannot translate it nicely, at least not yet. So I have things set up from the subframe, looking at this viewpoint, but I still haven't figured out the stone space thing, just to let you know. So that's still open. Okay, so that's my open question still. First of all, I have the result for extremal disconnectedness of Minel inverse, but I don't have a nice enough property using L. I have property using L prime. And I have no idea how to characterize that for rings and L groups. We haven't done that yet. And I still haven't characterized when it's a stone space. So that's still open. Another viewpoint, okay, the last one, and I have recently worked on this. For both Minel and Minel inverse. It's very interesting. Okay, so what happens is if you look at the compacts, it's a lattice, and therefore we can have filters of compacts. Okay, it's a lattice. And Zorn's lemma can be used to show you have maximal proper filters or ultra filters. Okay, and don't have to go through this, we're running out of time. So basically, we can construct ultra filters of the compact elements. So you have the frame L, right? And KL is a basis element, you can say. So you can have ultra filters of the compacts. Guess what? You can have maps bijection between ultra filter of compacts and minimal prime elements. And here's the relation, okay? You take an ultra filter, you look at supremum of the C perp for C in the ultra filter. All the C's are compact already. That is a minimal prime. And on the other hand, if you start with a minimal prime, look at all those compacts that are not below P, that will be an ultra filter. So there's a bijection, very nice. So you can study the ultra filters to study minimal primes. Also, guess what? I can endow the ultra filter with the two topologies, just like I did for min. I can have similar topologies on the ultra filter, the U's and the V's. And I have shown that ultra filter of K of L with the Hull kernel actually this is not called Hull kernel topology. This is actually called the Walman topology in literature. This is already known, but it's like the Hull kernel topology. It's the inverse thing happens. So it is homeomorphic to the inverse min, and the ultra filter with the inverse topology is homeomorphic to the Zariski topology of min. So they're homeomorphic to each other. So this is another viewpoint. You know, to study the Minel or Minel inverse, we can actually study the ultra filters with this similar topology. So yeah, so there are different viewpoints, you know, and we can look at that and figure out. But yeah, I'm still struggling with, and thank goodness for this talk. Actually, now I'm going back and I'm looking into this again because I totally forgot about that. I have an open question. When is Minel inverse stone space? All right, let's write another paper. Another paper can be out if we find the condition. So I'm still working with it. All right, so I think I'll stop. I have taken a lot of time. Thank you so much.
Thanks a lot for such a lucid talk, Papiya. And is there any question?
Purvita, can I just, because I'll leave now.
Yeah,
so
yeah.
If I am allowed to just ask. Papiya, I mean, after a long time, I met you and you gave a very nice talk. So thank you very much.
Thank you. Thank you, sir, for coming. I'm so glad to see you.
Second thing. Yeah. The question is related to categories. So
yes.
I was wondering what could be the relationship between this topology and inverse topology in the category framework, categorical
Yes.
framework. Have you
Yes.
ever thought about it, or can you say something?
I can say something. There's already a paper by Themba Dube, who is also my co-author and many papers. But Themba Dube actually worked on the category part of this right after my paper came out. This paper came out. So yes, so if you start with a frame, I think you have to have the category of algebraic frame with FIP and coherent frame homomorphisms. So not only frame homomorphisms, the morphism has to be such that the compact maps to compact. So that's the coherent morphisms. So in that category, you can have the, so you have the frame, right? And then you have the topology on mean L, which is also a frame.
Mm-hmm.
You see, there's a frame there. So yes, there can be, I think, a dense onto homomorphisms that will make the picture commutative. So I think, yes, there is definitely relationship. I'm not a category theorist, so I don't, I can't tell you exactly every detail, but yes. And guess what? I was really glad that Dube did this. For the inverse topology, he realized, and that's why the viewpoint that I have with the subframe, the same thing happens with the subframe. So you can have the categorical relationship between inverse topology and the L prime, the subframe of the L, with the same thing, the coherent map and then dense onto morphisms. Yes. There is something there. Categorical.
Yeah, okay. Thank you.
Yeah, sure.
So any more questions?
I have a question here.
Yeah.
It was very good to see you, sir.
Thank you.
Sir, again.
Yeah, Papiya, কখনো চলে এসো।
একদম স্যার। আপনি আছেন কলকাতাতেই এখনো?
হ্যাঁ, ভালো
আচ্ছা।
থাকো।
আচ্ছা। হ্যাঁ, Nonita, go ahead. Sorry, sir. Go ahead.
Yeah, the question is that, like, since I really don't know these things, I'm just asking. So you define the topology on the mean of L inverse, which is like so you're just taking is a complement of that topology in some sense that you are right. So you are taking u of x as x not less than equal to p, or I'm just saying less than equal to, yeah, and here x less than equal to p, right? All such x.
Yes.
In some sense, it's a complement of that. And also your definition of stone space is Hausdorff, compact and extremely disconnected. And then I'm just wondering, I'm feeling like one of the topology can't be Hausdorff, right? Like because of the denseness of the open set in some sense.
The inverse topology is not. That's why it was a complicated thing to make it Hausdorff when it is Hausdorff. Yeah, that one is not Hausdorff.
Yeah, then I did not get that. How did you characterize for going to characterize the stone space? How did you make that Hausdorff?
No, I'm not making it Hausdorff. I'm finding out what kind of property in a frame will make it Hausdorff and extremely disconnected. Both of them together.
Okay. So that's why you went to the ultrafilter for that? Like to get...
Yes, I was thinking maybe looking at the ultrafilter, that viewpoint might help. Not sure yet. But the reason for bringing in ultrafilter, there are other, because that's just another viewpoint. And in literature, you will find lots of things done with ultrafilters. So yeah, there might be something there.
Okay, so that's why it became difficult to characterize mean of L inverse as stone space, because it will no more Hausdorff, it will no more, extremely disconnected.
Exactly. It's not zero dimensional. It's nothing. Yeah. So it has very minimal properties to start with. So to make it a stone space, you will need a lot of different things. Yes. But it's also always interesting for any topological space to figure out when it's it has certain character. When is a Boolean space? When is it a stone space? So I just wanted to figure out a parallel result if possible.
And also
I think my hope is to find the characteristic with L prime. That's my hope, not with L, the subframe L prime, because categorically too, there is a relationship between them. So that's my hope. Go ahead. Sorry, Ranita, I was cutting you off.
No, I understood. Like I really enjoy your talk. This is really nice.
Thank you. Thank you.
and yeah, and also I did not hear about the term extremely disconnected before. So
Oh, okay.
I
Yeah,
did not,
so what happens, there are, lots of people who work on C of X, and I think there is a category now in AMS, they call it peculiar spaces, and I work on that a lot. So extremely disconnected kind of falls in that, lots of peculiar spaces, these P spaces, F spaces, all sort of things. The C of X people work on that a lot. Yeah.
so it seems like they are all totally disconnected, right? Like the totally disconnected is the necessary condition for being extremely connected, extremely disconnected. Right?
Yeah.
It seems to be like that. I just knew about the totally disconnected.
Yes. There are more, there are other disconnectedness. So extremely is pretty extreme.
Yeah.
And then there's a basically disconnected and yeah, also.
I was content. Like I was just up to the thing about, totally disconnected. After that, I did not know. So today I've received some idea about this. So I feel very happy. Like, yeah, things
okay,
like
good.
But yeah, it's like, I really like it. Thank you so much.
Okay. Thank you. No problem.
Any more questions?
Yeah. Please, Professor Sankapana.
No, you please go ahead. I will ask that.
I don't have a question, rather I have a comment. So in representation theory, people are looking at not just Zariski spectrum, Ziegler spectrum, but also Reb-Zariski spectrum. Have you heard of it?
No.
So Reb-Zariski spectrum has very similar definition to your inverse topology. So you might
say the term again.
It's Rep, R-E-P, Zariski spectrum.
Oh, okay. I have to look into that. Okay.
Okay.
Thank you for telling me. Reb-Zariski, huh? But very similar. You're not. You don't think is the exact same as inverse.
I will need to check the details. I haven't studied it properly, but I know it exists. It's the same. So whatever are your basic open sets, you convert them into closed bases rather than open bases, and you do the same thing. So I think it's the same. Like the development of L dash also looks sort of similar.
I see. Do you know do you know anybody particularly who has worked so I can look up or in this area?
You can find many references for this, I'm sure. Like so non-commutative geometry is related to this.
Yeah. Okay. It's nice to hear that there are other areas that people can work on these things, because that's okay. I'll definitely look up Reb-Zariski. Okay, thank you, Amit.
Professor Sankapana, you had the question.
You are muted.
Yeah.
You are muted.
No. Ami leave koche. I am leaving, so don't worry. Back away. Okay, thank you.
Please unmute yourself, Professor Sankapana.
Yeah,
now,
I did.
Yeah.
Can you hear me?
Yeah, we can.
Yeah. Thank you very much for your wonderful talk. I'm wondering if anybody has looked at any connection with Priestley spaces.
Yes. I think so. I am pretty sure, but I don't know much about it. Anything about it. I know that there are people who work on residuated lattices. They look at Priestley spaces. Yes, but I have not. I really have not looked at it, Professor.
Thank you.
So, is there any other questions? If not, then Papiya, I had some query. It's like you told that you can do parallelly the similar finding for L group and the ring of continuous functions. So I'm wondering that whether these areas are much simpler to look at it, or like, is there any, because
not simpler, but here's the thing. See, for L groups, I feel like it's simpler because there are extra properties. There's the addition in group. So those extra relations really help find things and prove things, which I don't have in frame. So that's why it's so frustrating sometimes. Like some of the concepts from L groups, I cannot translate because there's an addition and I don't know how to translate it in frames because that relation doesn't really translate. So in that sense, yes, I feel like whenever we go to L groups, yes, there are more things to play with. For C of X, it has the property that every prime is contained in a unique maximal, which is not there in frames, which is a wonderful, the C of X has a root system. That makes life so much easier. And guess what? Martinez actually have generalized that concept for algebraic frames. He calls it, I think, disjointification, just to be able to generalize more results from L groups to frames. But you have to have this extra disjointification condition, which I don't use. I try not to use it. I try to do as general as possible. But yeah, so that sense, probably a little bit easier. Yes. For rings, see, rings, yes, you also have addition there. But the thing is, you have to change everything in the ideal form. So every element in the frame, now you have to think of finitely generated ideals for rings. So if you do that, then it's not too bad. But then lots of extra thing comes up in rings, extra stuff. There are little differences, right? There is a principal ideal, there's a finitely generated ideal. Some things for frame, they're the same. See, for frames, they're the same. For rings, it kind of now branches into two separate concepts. Oh, something can work only for principal ideals. Something can work for finitely generated ones. And they're not the same. So again, some things we cannot differentiate in frame that you can in rings.
Okay. Okay. Yeah.
This is not a mathematical question. Do you know how Bhattacharjee is doing health-wise?
He is recently, and by recently I mean last couple of years, not doing very well.
Yeah, that's what I knew.
Yes.
Yeah.
I met him many times. I actually went to Canada where he lives. I went and met with him, and he was fine. But yeah, last couple of years I've heard his health has really gone downhill. I'm not sure.
90?
Excuse me?
He's close to 90 or something like
Yes,
that.
I think over. I think he's probably
Oh,
over
wow.
90.
Okay.
Yeah. And he will only travel to Cape Town every year. That was the only travel he would do. I don't know if that has stopped as well. I haven't heard about him because of this COVID. We haven't had any conference or anything, and I haven't heard from him since. Yeah.
Yeah, so I have shared some documents in the chat for you.
Oh, okay.
And you can have a look. So I think it was my supervisor who introduced that. I'm not sure about this.
I will definitely look into that. Thank you, Amit. Thank you. Okay, thank you so much. And if any of you, figure out the answer, let me know, okay? When is Minel inverse a stone space? No, really. Just share with me. Thank you.
No, it was such a nice talk, Papiya. And after a long time, I'm hearing you. So
yes, I know. It's been a while. Yeah, last year wasn't good for me. Yeah, and lots of losses. Oh, by the way, I should have mentioned, and somebody left. There's Blast coming up in June. If you guys know or not, BLAST. You can at least attend it. It's online. I'm hoping to at least see some faces, some of my well-known faces then. And I'm giving a talk as well. That's coming up. Just thought I would mention. And we are actually having a session in honor of Professor Martinez and Professor Charles Holland. He also passed away last year. We had 2 big losses last year. So we are having, in memory of them. But, yeah. Well, everybody stay safe, okay? It's really bad in India. I don't know what else to say. I just hope everything passes soon and this nightmare is over.
Yeah, we just need to hope for the best. And as Professor Shankapanar told us, that hope for a miracle.
Yeah. Yes. And it's like, my parents got both doses, but I still told them, please stay home. Don't do anything reckless at this point, because you never know. You can still get it. It's not 100%. So just be safe. So
that's true.
We hardly go out.
Yeah, I know. Where are you, Professor? Where are you?
I am in upstate New York.
Oh, I see.
Yeah, the name of Poughkeepsie?
Sounds familiar.
Okay, Albany, you know, at least
Yes,
you have
yes,
heard of, right?
yes.
We are halfway between Albany and New York City
Oh, okay, I
on
see.
the thruway, right?
Okay.
You know, right by the thruway. Yeah.
It's getting a little bit better, right, Professor, at New York?
Oh yeah, it in fact a lot better. You know, things
Yeah.
are opening up. Yeah, they are letting the games to be played now. You know.
Oh, okay.
Yeah. So
Okay.
and in New York City, a lot of things are opening up.
I see.
All
That's
the
good news.
shows are opening up.
Oh, okay.
You know, that's a big deal.
Yes, absolutely, absolutely. Yes, economy is just so.
Yeah, I mean, we are doing a lot better. Unfortunately, India is not, you know, doing well.
Yes, I know. Exactly. I know. Well, it was a pleasure. Thank you so much for inviting me, really.
Thanks a lot for
Nice meeting you.
Nice meeting you.
Nice talking to you all.
I think this is the last talk for this. What can I say?
Academic year.
Like,
Oh, that's right. Okay.
Okay.
All right.
We'll start on the July, I guess.
Have
right?
a nice summer, all of you.
Oh,
Yeah. Have a
You
safe
too.
Have a
summer.
nice, enjoy the summer.
Yeah.
Thank you. Thank you.